Okay, let's unpack this. We're diving into a stack of sources today, all focused on a surprisingly fundamental idea: how we measure shapes.
Yeah, specifically what the material tells us about quantifying their boundaries and, the space they actually cover.
Right.
And based on this material, our mission for you is to quickly kind of extract and grasp the core concepts, perimeter and area.
To get beyond just the definitions.
Exactly, to understand what the sources are highlighting as important about them.
It's like figuring out not just what length around and space inside mean, but what these sources say about why it matters.
Whether you're, say, estimating materials for a project or just trying to understand design principles.
Okay, let's jump into what these sources laid out then.
So the material starts pretty logically defining the basics. First up, perimeter.
The edge.
Exactly. The sources frame it as simply the total length of the boundary of a flat, two-dimensional figure.
Makes sense.
They mention standard units, meters, centimeters, and point out that conversion. 1 meter is 100 centimeters. Pretty straightforward.
Right, just tracing the edge. And the other core concept they hit is area.
Area. As the sources explain it, it's about the surface enclosed within that boundary.
Inside the lines.
Precisely. And this is where units become really crucial. We're talking square units now.
Like square meters, Anamono, or square centimeters, Siemena?
Exactly. And the sources, they make sure to highlight the unit conversion here too. 1 square meter isn't just 100 square centimeters.
Ah, right, because it's length and width.
You got it. It's 100 times 100, so 10,000 square centimeters. That simple squaring of the linear conversion factor, that's a key detail the material really emphasizes.
That difference between linear for perimeter and square for area.
Yeah.
Yeah, the sources definitely make that clear. Okay, so moving from concepts to actual shapes, the sources break down. The most basic straight-sided one they cover is the triangle.
The simplest polygon, yep.
Yeah.
For perimeter, the sources keep it totally simple, just add up the lengths of its 3 sides.
If the sides are A, B, and C, perimeter's A plus B plus C. No real surprises there.
None at all. But the area of a triangle, well, that gets interesting because triangles can look so different, right? Scalene, isosceles.
So what did the sources highlight about finding the area, given that variety?
What the sources really focus on is a common method using the base and the corresponding height.
What?
And they define height very precisely. It's the perpendicular distance, like straight down from one corner or vertex to the opposite side, the base.
Gotcha. Perpendicular is key.
Absolutely. The formula they provide is then half of the base multiplied by that height, so 12 base height.
Which points to something neat,
Yeah,
right? Like
pretty
even though
good.
triangles look different.
Yeah, this formula connects them all based on that specific perpendicular measurement. It's almost like seeing a triangle as half of a rectangle or parallelogram.
Which some sources hint at with diagrams, kind of showing how it fits inside.
Exactly, it links it back.
That's a great way to think about it.
Mm-hmm.
Okay, next up, a shape everyone knows, the rectangle.
Right. The sources confirm what you'd probably guess for perimeter. It's twice the sum of its length and breadth.
Or 2 times length plus breadth. You're just adding up the 4 sides.
Recognizing they come in 2 equal pairs. Simple as that.
And the area is even more fundamental for a rectangle, isn't it?
Oh, absolutely. The sources state the area is just length multiplied by breadth, L times B.
Straightforward.
But interestingly, the sources also make a point of mentioning the rectangle's diagonal.
Ah, cutting across corner to corner.
Yep. They show its length can be found using the Pythagorean theorem. Remember that. A plus B OTC.
Sure do.
So here, the diagonal is the square root of length squared plus breadth squared.
Which highlights maybe understand the inside of the shape too, not just the edges or the surface.
I think so. Especially when sources mention applications like in construction or geometry problems, that diagonal matters.
Bringing in Pythagoras definitely adds another layer. Okay. Simplifying further, the square,
Right. The sources describe the square basically as a special rectangle.
where all 4 sides are equal.
Exactly. So its perimeter is just 4 times the length of one side. Call the side A, it's 4A.
Makes sense. And the area just follows from the rectangle logic.
Yeah, even simpler. Side multiplied by side, so a squared.
Okay.
And just like the rectangle, the sources specifically call out the square's diagonal.
Using Pythagoras again.
It comes out as A times the square root of 2. The fact that the sources consistently mention the diagonal for both shapes.
Suggests it's pretty significant in the material, doesn't it?
It seems that way. Maybe related to stability or measuring across distance or just foundational geometric proofs they touch on.
Yeah, it feels like the sources aren't just, listing formulas. They're hinting at the relationships between them.
and their potential uses. They also briefly touch upon other shapes, didn't they?
They did. What else was mentioned?
The material mentions shapes like trapeziums, parallelograms, and rhombuses. It provides formulas for their areas, too.
We don't have time to dive deep into each one now,
But the key takeaway the sources seem to provide is that even for these variations, the concept of finding the enclosed area still builds on these same principles.
often relating back to rectangles or triangles somehow.
Yeah, usually through specific base and height measurements, just like we saw with the triangle.
So recapping, we've looked at these fundamental ideas, perimeter and area, the boundary and the enclosed space, and explored how the sources apply these to basic shapes like triangles, rectangles, squares, picking out the specific details and connections the material emphasized.
And understanding these measurements is just incredibly practical, as the sources sort of imply throughout.
Right, from estimating materials you might need for construction or crafting.
Or even just designing spaces, figuring out layouts. These concepts are really the foundation.
So here's a final thought, kind of pulled from the implications of these sources.
Okay.
How do these relatively simple, almost ancient ideas, just measuring the edge and the inside surface,
Starting with these basic geometric forms.
how do they become the absolutely essential language for designing, building, and understanding almost everything in our really complex modern physical world? Something to think about.